All right, welcome. I'm Mark Beierl, coming to you from outside of Toronto, Canada today. And so I'm going to be talking about highly available, production-ready OSM. So basically, OSM comes in a very small footprint and can be used very easily in demos and lab environments, and like the one that we just saw from Thomas and the team, where OSM is installing another version of OSM just for the purposes of being able to do some work. So that sort of environment, the OSM that was created wouldn't necessarily need to be fault tolerant, but the CSP level OSM, that may be something that would want to be protected. So I'm going to be discussing strategies and ways of being able to make OSM much more fault tolerant. So in general terms, what I want to do is describe fault domains. And in general terms, a fault domain is a group of software components that share a single point of failure. For example, when we talk about our OSM that's deployed, for person who's doing the development, not the primary OSM, but that secondary OSM, that entire thing could be just deployed in a single Kubernetes node. Went the wrong direction. A single Kubernetes node that's running on a single VM, and there we go. OSM in a box, everything's up and running. However, that VM would represent a single point of failure, because if you lose that VM, your entire OSM is gone. Or if you lose the server that VM is running on, the entire OSM is gone. So that in itself is a fault domain. That is an area that we need to look at. Okay, what can we do to protect this and make it more resilient? So there's more than one fault domain, and there's more than one way to slice it. So we're going to go through some of the concepts here. Okay, so we know one server by itself is a fault domain, but it also belongs to other fault domains. So there may be VMs that are running on that server. And if we lose that server, all those VMs go down. So maybe what we want to do is we want to put it into a rack, and we'll have multiple servers in that rack. But guess what? That rack is also a fault domain. Somebody could have been moving some equipment around in the lab and accidentally backed a forklift into the rack and took the entire rack out. So maybe we want to put multiple racks in a data center and spread these VMs out so that they're all across the data center. But guess what? That data center itself is also a fault domain. Is also a fault domain. We could lose the entire data center, in which case you would want to have another data center, geo-replicated data center, perhaps in another physical location. And you get the idea. At the hardware level, there are multiple things that can be done for the fault domains. So we'll take a look at Kubernetes, databases, OSM software itself, and an additional component of OSM, the VNF configuration agent. So taking a look at K8s clusters, we know that there are several components to Kubernetes themselves. We got the Kube API load balancer, the Kubernetes master nodes, and the Kubernetes worker nodes. And that's where the pods themselves will actually get scheduled and work will actually be done. And a good high availability design would be, say, to keep these separate from each other so that they are in separate fault domains. The next thing would be to go ahead and bring up another set of them and another set. So each one of them would be scaled individually, and each should be run as their own node in a rack. So the replicas should all be instantiated, and perhaps the replicas should each be in a rack or their own hardware fault domain. And something that goes along with Kubernetes itself is also a database, specifically etcd or etcd. So this is a database that goes along with Kubernetes, and it should also be set up with multiple replicas and be in their own sort of fault domains with their own anti-affinity rules. Maybe you want them on a different set of hardware, maybe in a different rack, maybe in the same rack. as long as it's all connected using a traditional spine leaf technology, there should only be one hop between any of your racks, and so there would be no performance consequences to this. So now, the OSM architecture. In terms of fault domains, here we have an overview of the architecture. We have a number of Kubernetes services, or pods, basically, that are going to be running in Kubernetes containers that are running the OSM software itself, and there's some common services that we have over here. On the left side is some databases. So two specific technologies, a NoSQL database and an SQL database, are being used here, and these by themselves represent a fault domain as well. So that's their own data fault domain. That means is that these things can fail independently from the OSM software. For example, if I were to lose the Mongo database, I could still talk to OSM. The NBI would still be running. It just wouldn't necessarily serve up any useful data because it couldn't find anything in the database. But the software of the NBI itself will say, hey, I'm alive. I've been started as a container. You know, maybe I'm not healthy. Maybe there's a health check that says, oh, you know, something's gone wrong. But it's a separate fault domain and must be monitored separately. So let's take a look at some of what can happen here with the databases and how we can protect them. So we have a very simplistic default deployment. We've got OSM software running, and we've got a single MongoDB database. So to make Mongo fault tolerant, we can go ahead and add additional instances of Mongo, and they can be started on different machines or different racks or wherever they go. And we put these together to form what Mongo calls a replica set. So these instances will all be configured, they'll all get votes, and they will vote for a leader among them, and you know which one's the primary and all that sort of stuff. And that all gets set up nicely. Now, remember what we talked about. That data center represents a fault domain. So maybe we want to add a second data center. So they could be replicated to a geographically different site. So this second site should then be configured so that it doesn't vote and it doesn't become a leader, because the last thing we would want is for a geographically replicated or distributed or you know, like 30 milliseconds of latency or however far apart these are. Last thing we'd want is for one of these to become the primary, and then OSM has to go through that to talk to the database. So we keep the voters and the primaries up here and the leaders up here, and down here we issue no votes. And only when the primary data center site is lost, we can then flip over and say, okay, secondary data center, you become the leader on Mongo, and we could have a second instance of OSM actually sitting in the secondary data center, and we could start that one up if the primary site was, if we lost the primary site for any reason, data center number one. There we go. We've got data center number two up and running. We've got OSM running here, and because it's the same database, it's going to be able to pick up operations right where the original one left off. So now that we have a fault-tolerant database, we've got fault-tolerant Kubernetes infrastructure, let's start looking at the OSM software itself. So any software that's running on this OSM server or running in this Kubernetes cluster, all the pieces of software are part of a fault domain as well. Yes, so here we go. Sorry, little click down here. The software domain for the OSM software. The fact that the NGUI is kind of outside of this box is a little bit misleading. What this means is that the web browser for the UI is outside of the box, but the actual service that serves up the web pages is inside of the OSM software fault domain. So yeah, that one's just a little bit confusing. Okay, so in a simplistic deployment, a client could communicate with the NBI service directly on the host port exposed by Kubernetes. This is great. We got one copy of the NBI, and the client can talk directly to it. But of course, that is a single point of failure. While Kubernetes itself may be spread across multiple nodes, if there's only one instance of the NBI running, then loss of the node that NBI is running on, or loss of the NBI container, would essentially would result in a complete loss of all services. So we should have multiple copies of the NBI running, which is great. Remove that single point of failure as there's multiple replicas available, but the client now would need to know, well, which copy of NBI is alive and working, and we got to figure out, okay, which one should we talk to? And that is where the Kubernetes Ingress controller comes in. So you add an Ingress controller and configure it, and then basically what will happen is the client can talk to the Ingress controller, and then that in turn decides which NBI replica it wants to send the requests to. Of course, these replicas themselves should be configured to have anti-affinity rules or whatever it is to make sure that no two of them exist in the same sort of hardware fault domain. And what I can do here is I'm going to do a quick little demo here. Here I've got a script running on the left, which is just simply over and over again doing an OSM Vim list every 4 or 5 seconds or so. And I have no Vim, I have nothing set up. And here we can see I have got one copy of the NBI running. So if I were to then go in and let me do a PS here. Okay, there we go. So if I go in and I kill the NBI process to simulate a failure, so let's do this really hard. We do a kill -9 of the NBI, and right away we can see, oh, we've lost that service. We've lost things that are going on. And if I take a look at the Juju status, you can see here that Juju is aware of that and is restarting the container automatically. There it came back. Okay, that's fine, but we still had an outage for this period of time. So if I now want to go in here and, scale this up to 3. So that's all it takes. I say Juju scale application NBI to 3 units. And when I take a look at the Juju status here, I can see there are additional pods that are starting up now to house the NBI. And from a Juju level, you can see, well, there's going to be 3 copies of them. This whole time that the additional scale up is happening, there's no impact to any of the service. And if we do that PS command again here, in a few moments, we should see that there are 3 of them running. And then I'll be able to kill this one right here, which is the one that we're talking to right now. And we'll see there will be no interruption in service. So let's see how we're doing here. Okay, config changed, leader settings, config. And if we take a look, there we go. Okay, we've got all 3 of them running. And I said that I was going to kill off the oldest one. So I can go ahead and do my sudo kill -9 on that one. And if I take a look at the Juju status here, oh, there we go, container error. It noticed already that, hey, it crashed. Crash loop back off, and it's going to automatically restart it in 10 seconds. But during this whole time, we've had no interruption in service because it was all taken care of. So back to our slide deck here. Yeah, so there we go. So the NBI should be configured to run, in different hardware fault domains, so that loss of even this entire rack would not give us any impact to our running software. Now for the VNF configuration and abstraction, which is effectively a software component inside of OSM called the VCA, and it is embodied by Juju, or a Juju controller that is part of OSM running software. So without the distributed VCA, all the charms are managed by this single Juju controller inside of here. And all the charms will need connectivity back to the Juju controller. So if you've got things running in multiple data centers, we're going to need to have two-way communication from each data center to where open source Mano lives, so that the proper communication and commands and everything like that can happen between the two of them. Additionally, proxy charms could then live far away from the workload that they're actually trying to manipulate. So if I've got a proxy charm for a PNF that happened to be located in this data center, that proxy charm would be executing an LXD cluster up here, talking over the network to the remote data center. That's not exactly the most expedient way of doing things. And of course, all of these ports have to be open and whatnot. So that represents a single point of failure for all of the charms. So what we could do is we could scale the controllers horizontally and then distribute the, there we go. Sorry, so we could distribute these and have additional VCAs co-located in the data center so that they're actually doing work directly with the OpenStack or Kubernetes or whatever it happens to be that are co-located with it. And we don't need to have that communication channel back to the central OSM. And instead, everything can be delegated here and running that way. So that would remove the requirement of having data center, the exposed ports and services between the data centers. The same principle applies to the proxy charms themselves. The containers in which they run can be made highly available by increasing the number of replicas and making sure that you have an HA LXD cluster with 3 nodes. In that way, when a node is lost, or even an entire, if the container is lost or the entire node is lost, the new container would take over, would elect a new leader, and service would continue normally. Resilience for Kubernetes-based charms is exactly the same way. We can use native Kubernetes technology for the storage and resiliency, as well as auto restart. Now I'm going to take a bit of a moment and just briefly talk about security in OSM. One of the main things with security attacks on the internet, people keep on seeing, oh, somebody got into my webcam because, well, I didn't change the default user, or it came with a hard-coded password and I never changed it. So OSM has been taking steps towards mitigating these type of risks. There's in Charmed OSM, there will be no default password. It is a random password that's generated as a 16-digit or character hexadecimal string. And of course, OSM itself secures all of the private keys in the database, all of the private keys and passwords and everything in the database before they're stored. So we are using encryption at rest for these things. So going hand in hand with that then is we've also changed OSM so that the containers no longer run as root. Running the containers with non-root adds the extra layer of security, because now even if I manage to compromise the container and get access to commands in the container, I can't do things like install new software. Like maybe I would want to do an apt install OpenSSH server and start that up so that I can SSH into the container and do bad things to it. I can't bind to unprivileged ports. I can't modify any of the installed OSM software. Before, when the container was running as root, if you managed to compromise the container, you could actually have changed some of the Python source code that was running in the container and cause it to execute arbitrary commands. With this running as non-root, of course, all of the software is installed as a particular user, or maybe as root, and then the user is what's left running in the container, and that user does not have permissions to modify any of the files. So Charmed OSM is an upstream installer. It is the same installation pattern. You just do, download the download the OSM installer and just add the Charmed flag to it. And the difference between this and the Kubernetes installer or default installer is that OSM services, NBI, etc., all of these things are deployed as charms, which is what you saw on my one screen basically over here. You can see each one of these services is a charm that was deployed using Juju. And when we do that, we can add Juju actions to things, which allow us to be able to scale our, what you saw earlier, where I added a new replica and things like that. So the way you can do day 2 operations on OSM is simplified by the fact that we use Juju for OSM itself. It takes care of the management of the Kubernetes ingress, and the Charmed option also has an HA bundle automatically in it that will deploy with multiple replicas of the parts of the OSM software that are capable of running in HA. So you can do Charmed install with just a single node, or you can have it in HA where it's going to install many replicas. And once we have that sort of thing, as you saw, the ease of scaling applications, we can just go ahead and say Juju scale application NBI to 3 units, and we'll get additional copies of it running. I could say 5, I could say 1, I could say 0, and that would stop the NBI, and people would no longer be able to talk to OSM as long as there were 0 instances running. So in the case of that multiple data center that we talked about, where you have a standby OSM in a second geographic redundant site, you could just scale all the services to 0. And then when you've detected that the primary site is no longer operational, you can then scale up the instances without having to install OSM, and they'll just go ahead and start up and be available for running right there and then. Database connection strings. If you wanted to have an external Mongo database and an external MySQL database, because your IT department already knows how to set up a production-grade Mongo replicated, geographically redundant cluster, and they go, okay, we've installed it. Now, how do we make OSM work with it? Well, that is also a simple Juju config string, where you can just say, hey, your MongoDB URL is, and give it the information. There would be commands as well, configuration for the credentials as well that you can put in there so that you can authenticate with the Mongo database. But it is simple as that. The Charmed installer can be, the charms for the NBI and RO and all of the other services can be told where to find their database if it's external. Virtual hosts for the Ingress controller. This one is a little bit more subtle. When you talk to the Ingress controller, it is listening on one port on one virtual IP. So that's 443. We've got SSL enabled, and by the way, it's really easy to properly secure this with an SSL certificate as well. So how does the Ingress controller know when to go to the NBI versus when to go to the NGUI? Well, that is done through the use of a site URL where you put in some sort of string here. In the Hackfest, we've been using Route 53 for some of these things. In other cases, you may have seen the use of nip.io. nip.io is a free service which does nothing more than takes the IP address that is in front of .nip.io and returns that as the DNS host IP address. So if I say, you know, I want to look up 127.0.0.1.nip.io, I'm going to get back 127.0.0.1 as my IP address. And so if you put, you know, NBI with the NIP in front of it, or UI, then the Ingress controller knows which one it should go to. So then the client can just simply refer to it by a DNS name, and the Ingress controller will investigate, okay, what's the pattern match, and dispatch the service accordingly. And lastly, if you already have a hardened production-ready Kubernetes cluster, and you already have an existing LXD cluster, you can also deploy OSM to that by giving it the kubeconfig YAML. Or if you have the LXD, you can also give it the LXD YAML, or both of them, depending upon, you know, mix and match as need be. So when OSM you know, when the install script goes to run and it sees, oh, you've given me a kubeconfig YAML, it's not going to attempt to install K8s or any form of Kubernetes, but instead will deploy the OSM pods directly to that existing K8s cluster. Same thing if you gave it LXD cluster information. When it goes to deploy any proxy charms, it will use your existing LXD cluster instead of trying to configure a LXD cluster locally. So with that, I think I'm over time, but I am done. Are there any questions?
Thank you so much, Mark. Thanks for bringing these issues that we usually face in production environments. Like, do we have any questions?
Yeah, maybe just one quick question. Yeah, first, thank you, Mark. Really, it's really very nice presentation. Just if you go to slide 11, where you replicate the VC component.
Yes.
Okay. Yes. Yeah. Next. Yes. Here. Yes. Yes. Exactly. Okay. Yeah. So here the two VC components are connected to each other when you replicate them. Like when you replicate each of them at data center 1 and 2. Are there any connection between the two VCs so they can synchronize, or just to they provide some feedbacks or some updates between both of them?
Okay, so basically OSM is the one that will coordinate each one of these, and each one is going to be seen as their own controller. So they don't necessarily, like at the Juju level, they're not going to be aware of each other.
Okay.
Yeah,
and
so
go ahead.
So yeah, I mean, it's kind of the N2VC who will do the marshalling and say, you know, do any sort of coordination between multiple VCAs that are necessary.
Okay, and yeah, at slide 15, you was referring to the non-root privilege.
Yes.
Yeah, so you was referring to the non-root user privileges here for the OSM containers. So this can actually protect against the privilege escalation vulnerabilities, or this is just like for the protection of some other type of vulnerabilities. I mean, with such capabilities, is there a way to protect against the privilege escalation attacks in the OSM system?
So yeah, I guess there's two parts to that privilege escalation. Within the container, this prevents privilege escalation from inside the container. So let's say, for example, the web UI. Maybe because it's HTML and HTTP and those sort of things are, you know, notoriously hard to protect or hard to lock down. Maybe there was some way we got ourselves a bug inside of the NGUI that allowed for arbitrary commands to be executed in the container due to some sort of cross-script vulnerability or overflow or something.
Mhm.
So by running a container as a non-root user, we prevent the escalation of privilege where they won't be able to install new software in the container or modify any of the existing software. Like say they manage to find out a way of giving a carefully crafted network service descriptor, and we're doing a post of that to the NGUI. And maybe in that post, somehow we manage to break it so that when that gets unpacked, it's going to overwrite a file that is used by the NGUI itself to render some display. So now we can inject code into the NGUI. Because all of the files are owned by root, and the process, the web server process that's running is running as non-root, you won't be able to modify any of the files and be able to inject anything that way. Now, preventing in OSM me as a regular user from getting access to a different tenant or escalating my privileges in OSM, well, running a container as root or non-root will have very little impact there. That's an application level vulnerability. And that's something, you know, that would need to be mitigated in other ways. So make sure that there's proper ACL checking for every action that's done in OSM, et cetera, et cetera. So.
Okay, yeah, thank you, Mark.
You're very welcome.